Okay, so good afternoon, and my name is Tomoko Matsuo, and then I'm going to go over the basic of data simulation, and also talk about application to high-latitude electrodynamics. So there's a bit of overlap with Rutger's talk, but hopefully I'm going to give you a different perspective to understand this algorithm, its mathematics behind it. Okay, so as everybody knows, the data simulation is about combining sources of information, one coming from prior knowledge of the system that often come from model, like Rutger was saying, and then also could come from empirical models. That's the case with AMIE, assimilated mapping of electrodynamics application. It's come from empirical model. Good thing about this prior information is it is complete in space and time. On the other hand, the other source of information is observations. As you know, observations are sparse in time and space. And then by using this sort of math behind it, we could combine these two sources of information to get complete information about the system. And then hopefully we could do it optimally. And I'm going to talk about how you could do it optimally. And then there are many different kinds of data simulation schemes and inverse method. One way to understand, it's really convenient way to understand is it's called Bayes' theorem. And it's a really basic concept in statistics, and I'm going to kind of go over this. And then what Bayes' theorem says is that how to combine these two sources of information is that, let's say like you have prior information. It is stands for probability distribution of, the temperature of this room. And then say you have observation of temperature of this room, for example. And then like a posterior information. So it's basically data simulation analysis is actually proportional to product of those two PDF. And then, I know like if you heard about this for the first time, what is it? But actually what we actually do in daily life. For example, let's say like this green line represents the prior information about temperature of this conference room. And then, so let's say I made a phone call to, how much, what's gonna be the temperature? And then like I heard that sometimes this room has air conditioner on, and then in most of the case, air conditioner is on, so it's a degree Celsius. And then like it's broken, so temperature gets quite high. Okay, so before I come in here, I have this information about temperature of this room. And then like once I arrived, I stick out my thermometer and I make my own measurements. This is observation, this is represented by red line. And then product of those two PDF is a white line represent posterior distribution. So we kind of do it intuitively, how to assess that those information that what we have before and what we know after making observations. Okay, and then like to connect those Bayes' theorem to whatever the equations you have you are shown to like Kalman filter. One of the important assumptions most of data simulation schemes makes is Gaussian distribution of this PDF. So this represents normal distributions. If you want to specify Gaussian distribution, you need two sources of information. One is mean. You need to know what the mean is. And the second one is variance or covariance. If you have variables more than one, you need a covariance. So those are the two parameters. So this is the mean and then covariance that gives the spread around the mean. And that you could have the same thing for the observations. And then so if you have actually conveniently product of those two Gaussian distribution, if you look at the equations, it actually product of two Gaussian is Gaussian. So luckily we have posterior distribution. It's actually end up being Gaussian. It's interesting. And then so Gaussian posterior distribution, that's data simulation analysis. Mean of this Gaussian distribution is x of a. That Kalman update equation. If you remember, the Rutger's slide had exactly the same equations, actually same notations, I think. And then also covariance expression is given here. And the Kalman gain, it's these expressions. Okay, to get this closed form, you need normal distributions, that's one thing. The second thing you have to know is that we assume that observational operator, which is H, which is map state let's say, electron density information in a grid to the observation location. For example, it could be simple interpolation. And that H matrix is linear. If you have that, you could have closed form. And actually, you could get this common filter equations. And then AMIE application you're going to hear in later slides is actually we're using this common update equations. We don't have common forecast step, but we use update, okay? So remember that, I'll come back to that. Okay, so now I just want to spend a few more slides to explain what this mysterious terms of covariance. It's easy to understand variance, but the covariance, what is it, okay? So let's think about two variables case. What could be a good example? Okay, so two variables. This gas price in Colorado and the gas price in New Mexico, for example. And then, so it's like this x-axis is that distribution, prior information about gas price in Colorado. And then let's say that gas price, the next state, each other are correlated. And that relationship is given by prior covariance. So this is 0.225 that gives the variance. That's like a width of this Gaussian curve. And then second, this term tells the spread of this y-axis. So and then like this off-diagonal element tells that correlation between those x variable 1 and variable 2. Okay, and then let's say that I only have observation of the x1. And that's what it means. So it's x1 is observed, and then x2 is not observed. Okay? And then like going through this Bayes theorem, we actually can make an update to the unobserved variables. So that's represented by white lines, this PDF of x1 and x2. And then, for example, it's easy, for example, if this off-diagonal element is 0, that means there's no correlation. We don't really have, so if you see that like line here, there's a tilt in this joint distribution. Right? If this is 0, there's no tilt. So there's no information actually can be mapped to that x1 to x2, right? Okay, so that's one way to understand the role of covariance. We could actually make an inference based on using covariance from observation to unobserved variables, okay? Okay, and I'm gonna explain different way what actually covariance is doing. So I could explain this in a spatial sense. Okay, so let's say there are two different types of correlation function. It might be easier to see, okay? So this x-axis is lag distance, and then, so the left hand has a correlation scale that actually falling off quite rapidly as you get away, 2 points get away from each other. And then the other case, correlation function has actually slower separation fall off. And let's say like I could generate a random field using this correlation function. And then, okay, so this left, so I'm gonna show the few cases, the one case, second, and third. You see? So it's like so left hand side, it's this random field has shorter correlation length scale, and the right hand side has longer correlation scale. So this is a random field, and we want to know underlying correlation length scale, right? And then, okay, so so this is a stationary case. Covariance is the same everywhere. So you get this kinds of random field. And then this is correlation length scale is different, but its correlation is same within the domain. And I created this random field, which is combination of those two. And then let's estimate that 2D correlation function. So let's say the correlation function with respect to the point, so indicated by red, looks like this. So it's like anisotropic, and that's like this. And then a far right side, like correlation length scale with respect to this point has longer scale, right? And then in the middle has sort of kinds of somewhere in between. So like if you're doing a spatial analysis, you actually really want to use the correct covariance or correlation length scale for example, if you have observation here, like somebody asked, Martin was asking that, like, let's say this red point is observations, and then we don't know anything about the rest. And then, like, we want to spread the information as accurately as possible. And then, for example, if you use a different correlation function, from correct in this domain but incorrect, we're going to actually spread out information incorrectly. So that's really importance of covariance. We want to get the mean state right, but also covariance has to be very accurate, as accurately possible. Okay, so that's the role of covariance. And then, okay, I'm going to switch the gear to the high-latitude electrodynamics now, so be prepared. Okay, so assimilated mapping of ionospheric electrodynamics is inverse procedure to infer maps of electric field, potential, and then currents, and then magnetic field perturbations. And then you could derive geoheatings and then Poynting flux as a combination of those. And we infer those from observations of all the variables. So different type of observations. And I'm showing one snapshot of the collection of observations. You can see, like in this area, it's ground-based magnetometer data. And then this is DMSB flying through this area, and then measuring plasma drift, right? And then somewhere here, like HF radar is given also measurements of plasma drifts. So AMIE combines those two observations with prior information, and then get the optimal map of, for example, this case, potential, electric potential. And then why we need the data simulation is that, for example, high-latitude electrodynamics, it changes so rapidly. This is a storm case. I'm showing every 5 minutes snapshot for a few hours. And we are not there. I mean, model is getting really good, but we have really good observations. So we like to make best use of observations. And then, like, we would like to get the complete information of polar cap electrodynamics. Okay, and then so that's the goal. And then now I'm going to explain that how AMIE actually combine those different observation types to get a coherent map of electrodynamics. Okay, so AMIE doesn't actually analyze those data independently. We actually use linear relationship among those variables. Okay, so let's say, like, that means if I know electric field, I could map the information to different parameters, and that assumption that conductance is known, right? And let's look at that a bit more carefully. What's going there is the first equation is just an electrostatic field. This is potential, and then take the gradient, and then you can get the electric field. It's simple. And then the second equation is Ohm's law, right? And then given assumption that we know the conductance in advance, so we could map back and forth electric field and then currents. Of course, this is a limitation of AMIE procedures, and then you student, you're inspired, you could help us to actually, this is a really important area that you could actually contribute to get really good conductance. And okay, so for now, we make assumption that conductance is known. And then this is current continuities. So horizontal currents is actually, this is a field line currents, and take divergence of horizontal currents, and then, we know both. And then Biot-Savart's law going back and forth, magnetic perturbations and the currents. And then all the things you probably learned in your physics class, I guess. So it's quite accessible physics there. But so that's important thing. We use linear relationship among those parameters. The second important thing to understand AMIE is we are not actually solving the grid points electric fields. We're solving in terms of spherical harmonics, right? So let's say what that means is that, like, now let's say that X represent spherical harmonics coefficients, and then psi represents spherical harmonics, some kinds of basis functions, right? And then phi is potential. And then, for example, using this linear relationship, once we prescribe potential in terms of spherical harmonics, we actually can describe the electric field in terms of spherical harmonics too. And so we could actually plug this information into this. Let's say F represent the linear relations among those different parameters. You can get this expression. So I like to make a connection to the basic data simulation equations. So AMIE is solving, basically doing a Kalman filter update of spherical harmonic coefficients. And then we only need one set of coefficients because we can map back to all the different parameters through this linear relationship. Okay? So this is a basic of AMIE so far. And I'm gonna go through 3 more slides about how you could, what would be new ideas to improve AMIE. And then one thing is, like, I spent quite a bit of time in the importance of covariance. And then AMIE doesn't use physics-based model. So we don't really have really time-dependent covariance, let's say. But we can make covariance time-dependent using observations. So that's what I want, one idea I like to explain. Okay, so let's say this is a Kalman update equations and Kalman gain. And then let's say background error covariance, has some parameter, here is alpha. And then we can make it adaptive. And then we can come back to this later, but all the things you need to know is that we can estimate alpha by minimizing this cost function, let's say, right? And it is actually quite neat. So the D has, we call it innovation. So innovation vector is basically this part, discrepancy between observations and climatological prediction, right? And so basically this part has observations. So we by using observations, we can estimate the best alpha. So like each time we get observations, we can make this background error covariance adaptive. So that's the way we can make background error covariance flow dependent. So like it's hard to see it in the equations, but let's explain it. I'm going to explain it visually. So this is a result from the maximal likelihood estimate. Let's say like I have these kinds of set of observations, and then using that I could make a covariance adaptive. And so this is the result. So it looks like it's just 2-cell convection patterns, but this is exactly your question, which is quite good. That like let's say I have observation at this red point, and this is how the information gets spread out into all the 2D domain, right? So this is the role of covariance. And I'm saying that there's a bit of math involved, but then it's not. If you get it through, you could make this background error covariance dependent, so that you can get a really good. You can get a good analysis. So this is different locations at different time, right? So it's space-time dependent. Okay. So that's one idea to improve AMIE. Okay. And another idea to improve AMIE is to use different kinds of smart bases. So spherical harmonics, as you know, I mean, if you know, I don't know, maybe you are not exposed to it. So it has, spherical harmonics has 2 components. The basis function is defined all over the globe. And then like this part is associated Legendre function. And that determines latitudinal distributions, right? And then this part is cosine and sine, and you probably know. And so that's kinds of product of those 2, and then get this kinds of space-time 2D basis functions, so spherical harmonics. So it's defined everywhere. So we call it has a global support. And then it is actually great to spread the information. But also if you have like a very high resolution local observations, this is not really flexible enough. So this is other idea that we could use is compact supported basis functions. Then, for example, wavelets. And then wavelets is a collection of basis functions. Actually, it's made up of sort of scaling and translation. So it's the same shape. It's kind of shifted into the horizontal direction. So this is a base, like looks similar, and that's basically frequency of these waves gets half and a half and a half, so it's scaled, and that's kinds of simple functions, but we could use this kinds of function to describe these states better. So that's a second idea to improve AMIE. And then other new idea is that AMIE solves the minimization problem in terms of electric field. So that means we map all the observations into the electric field, and then we do the minimization in the electric field. But we start getting really interesting, new type of observations. And for example, we are very excited about Ampere, iridium constellation of all the satellites. We get all the bunch of magnetometer on the 66 satellites and have like really dense observations. So now we can actually do the minimization in the different quantities. And then also we could actually talking about do it in both, minimize both rather than mapping to one or the other. So that's another idea. Okay, so it came to the summary, and then I explained that data simulation methodologies, most of them you can understand in terms of Bayesian statistics framework, and that gives sort of good overarching sort of framework. And then important things is that we make assumption that the PDF is Gaussianly distributed, and then also observational operator H is assumed to be linear, or can be linearized, I guess, linearized. And then I also, covariance is important, especially in a type of application like AMIE. We don't rely on a dynamical model, okay? And there are a few points that we could actually improve this assimilative mapping of ionospheric electrodynamics, and then we could actually go from global function to compactly supported functions to get a better resolution of final analysis. And then also to take advantage of new observations, we could actually minimize in the different quantities. And then, of course, we really have to improve the conductance models, and then final idea is make covariance adaptive. And then any of the ideas need a lot of contribution from next generation. Okay, that's all I have to say.